Welcome. Today I'm going to tell you a detective story. The case of the missing neutrinos from the sun. Let us begin with the beta decay of the neutron. A neutron decays to a proton, an electron, and a neutrino. Well, actually, this has to be an antineutrino. Inside the nucleus, a proton can decay to a neutron, a positron, electron with a positive charge, and a neutrino. Now, why a neutrino versus antineutrino? Well, there are three particles which are very light. These are known as leptons, and electron was the first lepton to be discovered. Now, and then of course, there is an anti-lepton, which is the anti-electron or the positron. Now, for each of these, you assign a certain lepton number. The lepton number of the electron is +1, and the lepton number of the anti-electron or the positron is -1. Now, let's look at this equation over there. A neutron is a heavy particle, and on the right-hand side also, there is a heavy particle, so that is fine. So the baryon number is conserved. But the left-hand side has no lepton number, but there is an electron here, so the lepton number of the electron is +1. In any reaction, all the quantum numbers have to be conserved. Therefore, because the lepton number of the electron is +1, I must put a neutrino here, which has a lepton number of -1, which is why it is an antineutrino. But in this reaction over here, you notice that it is a positron. Positron has a lepton number of -1. Therefore, I am allowed to put a neutrino, which has a lepton number of +1. So let's proceed now. Now let's go to the center of the sun, where hydrogen is being fused to helium. This is how the sun generates energy, and we have discussed this in great detail. The first step in that reaction is that two protons combine to form a deuteron, which consists of a proton and a neutron inside the nucleus, and of course a positron and a neutrino. Now, as I explained to you before, this reaction is extremely unlikely process and will happen only once in about 10 billion years. But on the other hand, there are 10 to the power 57 protons in the sun. Therefore, even with such a small probability, this reaction will happen. And if it didn't happen, the sun wouldn't be shining. Well, once you have done that, the next step in the synthesis of helium is very straightforward. The deuteron combines with the proton to form a helium-3 nucleus, and a gamma ray is emitted. And now begins our story. What I discussed in one of the early lectures is that now two helium-3 nuclei combine to form a helium-4 nuclei, and then there are two protons. So we started out with two protons, we ended up with two protons, and in the process we have created one helium-4 nucleus. But what I didn't tell you at the time is that this happens only 85% of the time. There are two other branches of this reaction, and in branch 2, which is roughly 15% of the time, helium-3 nucleus combines with the helium-4 nucleus to form beryllium-7, and then the beryllium-7 decays to lithium-7, and then the lithium-7 decays to 2 helium-4. Please don't worry about this detail. I just want you to know that there is another route for creating helium-4 nucleus. And then there is an extremely improbable branch 3, which has a probability of 0.01%. And in that, a helium-3 and helium-4 nuclei combine to form beryllium-7. And the beryllium-7 then becomes boron-8, and the boron 8 decays to beryllium 8, and then the beryllium 8 decays to 2 helium 4 nuclei. So I know that I'm hitting you with all sorts of things that I haven't told you before. It is not important for you to know these details. I just want you to appreciate that there are 3 branches of producing helium 4 nuclei, and in each of these branches, neutrinos are produced. And the neutrinos produced in branch 1 and branch 2 and branch 3 have very different energies. And this matters when you try to detect the neutrino, because you have to make a detector which is not only sensitive to neutrinos, but which is sensitive to neutrinos of a particular energy. So it is for that reason this is important. Just keep that in mind and forget about all these details. Now, how do we know that all these things are true? If protons are in fact being fused into helium, the only witnesses to this reaction are the gamma rays that were produced, 2 positrons that are emitted for each helium-4 nucleus that is produced, and neutrinos, 2 electron neutrinos. Please keep this in mind. The only neutrinos that are produced are electron neutrinos and not antineutrinos. This is very important to keep in mind. Now, if it is true that the sun shines because it is converting hydrogen to helium through these branch 1, branch 2, branch 3 processes, then the sun must be emitting 10 to the power 38 neutrinos per second. 10 to the power 38 neutrinos per second. So a good fraction of these neutrinos pass through the Earth and indeed are passing through you every second. And what we want to do is to be able to detect these neutrinos to really prove that these reactions are taking place. Now, you may say, what about the gamma rays that were produced? It is true, gamma rays were produced, but these gamma rays, due to absorption and re-emission, as they diffuse out towards the surface of the sun, get degraded, and when they eventually leave after some 50,000 years, they've been degraded from gamma ray energies to about 1 electron volt or so, which is the energy of a visible photon. That is why the radiation that is coming out from the surface is mostly visible radiation. What about the positrons? You produce 2 positrons, after all, for every helium-4 nucleus that is produced. Well, the positrons will immediately meet an electron and get annihilated, and therefore they will produce more gamma rays, and these gamma rays will scatter, and they essentially contribute to heat, and these positrons have no chance of ever escaping from the sun. So that leaves us with the neutrinos. And the neutrinos can escape and will escape and do escape. But unfortunately, as we will see in our story, they are what they would call as hostile witnesses. You cast them, you put them in the witness stand, and they turn hostile. So let's try to understand the story properly. Now, the reason why neutrinos can escape, and this is also related to when you try to detect the neutrinos, is that the neutrinos have very long mean-free paths. The cross-section for neutrino scattering is given by this expression. Please don't worry about this expression. What matters is the mean-free path of the neutrino. Mean-free path is the distance traveled by the neutrino between 2 successive scatterings. Now that mean-free path for the neutrino is 2 times 10 to the power 13, 2 times 10 to the power 20 centimeters divided by rho, where rho is the density of the matter. Now, if you consider matter at the density of lead, then the neutrinos can pass through 100 light years of lead without any difficulty. So that tells you what an enormous mean-free path the neutrinos have, or in other words, what a small cross-section neutrinos have for scattering against anything else. Around 1960, a chemist by name Raymond Davis with strong encouragement from a very young theoretical astrophysicist by the name John Bacall, decided, I'm going to find these neutrinos that are produced in the sun. So let me tell you about this wonderful experiment that he thought of and he actually did. What he did was to get himself a gigantic container and filled it with 100,000 gallons of carbon tetrachloride. Now, carbon tetrachloride is what your dry cleaner uses when you give your sari or a coat for dry cleaning. 100,000 gallons inside the tank. Now, because you're trying to detect a very elusive particle, and there can be all kinds of other disturbances, you want to minimize these other spurious detections. Therefore, what he did was to put this laboratory with this gigantic tank of carbon tetrachloride in an underground tunnel, 1,000 meters underground, in an abandoned gold mine in Homestead in United States of America. Now, the name of the game is the following. Neutrinos scatter off chlorine-37 and they produce argon-37. So the way you know a neutrino has interacted with your detector is that there is an argon-37 nucleus. Now, argon-37 nucleus is itself radioactive, but we won't get into that story. Now, so the name of the game is to count these radioactive argon atoms. Now, just to give you a flavor for how extraordinarily difficult, indeed mind-boggling, this attempt by Raymond Davis was, every few months he would analyze the liquid in his tank and try to find this radioactive argon-37 atoms. And he would find about 15 argon atoms. 15 argon atoms out of 10 to the power 30 atoms inside his tank. 100,000 gallons has 10 to the power 30 chlorine atoms. In that, he is trying to find 15 argon atoms. So that is much worse than trying to find a needle in a haystack. But he did find them. Now, what kind of neutrinos was he trying to detect? What is plotted here is, on the y-axis, the flux of neutrinos that you expect from the sun as a function of the neutrino energy. In the x-axis, energy increasing from left to right. This is 0.1 MeV, this is 1 MeV, this is 2 MeV, and this is 10 MeV. The important, and here are the reactions that produce the neutrinos in the sun. Don't worry about that. All I want you to appreciate is the red arrow over there. That is, the chlorine detector, which Raymond Davis used, was only sensitive to neutrinos with energy greater than about roughly 1 million electron volt. So Raymond Davis's experiment could only detect neutrinos from beryllium-7 decay to lithium-7 and boron-8 nucleus to beryllium-8. And these have energies in excess of 0.86 MeV. They are in that region. But please note that the flux of these neutrinos, shown by these two curves, is extremely small. This is a logarithmic plot. So the flux of these neutrinos produced by these reactions in the red rectangle, or the flux is incredibly small compared to the flux you would expect from the neutrinos produced in the proton-proton chain reaction. See how enormously high this flux is. But the chlorine detector is not sensitive to these low-energy neutrinos. So what do? You do the best you can. So you try to detect this neutrino. And the first results were announced in 1968. I remember this very clearly. I was a student at the University of Chicago at the time, And every Thursday, some distinguished person will come and give a colloquium. One Thursday, Raymond Davis came and announced the first results from his experiment. And this is what he announced. The results are expressed in what is called as the SNU. SNU stands for solar neutrino units. And one solar neutrino unit is 10 to the power minus 36 neutrinos per second. Remember, the sun is emitting 10 to the power plus 38 neutrinos per second. The unit of detection is 10 to the power minus 36 neutrinos per second. So that is how small the detection probability is. The threshold for the neutrino absorption in the chlorine experiment, as I already mentioned, is about 0.8 million electron volt. Now, the neutrinos from PP reaction cannot be detected, as I already said, because they have much lower energies of the order of 0.2 MeV or so. So the experiment can detect neutrinos from the decay of beryllium-7 and boron-8, and only these two decays. The predicted rate of neutrino detection, remember, that depends on what fraction of the neutrinos emitted by the sun passes through your detector, convolved with the probability of detection in your carbon tetrachloride tank. Not every neutrino will actually hit something and produce an argon-37 nucleus. So if you do all that calculation, then the predicted rate is 7.9 SNU with the error bars that are indicated there. There are two errors. One is the statistical error, the other is the systematic error, but I won't dwell into that in this particular lecture. So that's the expected rate. And what did Raymond Davis find? He found 2.1 plus or minus 0.9 SNU. Therefore, the discrepancy between the predicted rate and the observed rate is much greater than the error in his measurement, which is only of the order of 0.9. Look at the difference. Therefore, Davis had detected only about 1/3 of the argon atoms that were predicted by theoretical calculations. In other words, he had only detected 1/3 of the expected number of neutrinos that you would hope to detect in your experiment. Now, what was wrong? Well, one possibility is perhaps the theoretical calculations were wrong. This might either be due to the predicted number of neutrinos being wrong. In other words, Hans Bethe's calculation, for which he had got the Nobel Prize in 1967, those detailed numbers are wrong, or the calculated production rate of argon atoms in the detector could be wrong. You were too optimistic in thinking that you would detect so many neutrinos, but you shouldn't have been so optimistic. This is one possibility. The second possibility is that something is wrong in the experiment. And the third possibility is maybe there is something wrong in the fundamental physics that goes into fundamental nuclear physics. So there are all these three possibilities that you have to be examined before you can pass a verdict on why Davis detected only 1/3 of the neutrinos. Now, let us digress for a moment. First, there was the neutrino associated with the electron. The electron neutrino and the electron antineutrino, which is associated with the positron. Besides the electron, there are two other light particles, two other leptons that were discovered much later. One is the mu meson, which was predicted by Homi Bhabha and discovered later on, and then the other is the tau meson. Now, associated with these two leptons, the muon and the tauon also, there are neutrinos and antineutrinos. There is a muon neutrino and an anti-muon neutrino. There is a tau neutrino and anti-tau neutrino. So the neutrino family actually consists of 6 neutrinos and not just the electron neutrino and its antiparticle. Please remember that in Davis's experiment, he could detect only the electron neutrino, but that was okay because the sun only produces electron neutrinos. It does not produce electron antineutrinos, nor does it produce muon neutrinos or tau neutrinos. You remember the reactions that I showed you. Keep this in mind. The experiment can only detect the electron neutrino, but that was fine because the sun only produces electron neutrino. But please keep in the back of your mind that there are other 5 neutrinos belonging to the neutrino family. Now, at that time, an Italian physicist by name Bruno Pontecorvo, who had left Italy many years earlier and was living in Moscow, in Russia, said something very radical and revolutionary. So he said, look, something happened to the neutrino as it left the sun and traveled towards the earth. The neutrino suffered from a personality disorder. So you're having a big party in your house. You invite Dr. Jekyll to the party. He leaves his house to come to your party. And before he reaches your house, he has transformed himself into Mr. Hyde. So your watchman will not let him in because he is not Dr. Jekyll, but he is Mr. Hyde. So there's a personality disorder. So Pontecorvo suggested that maybe neutrinos have personality disorder, like between Dr. Jekyll and Mr. Hyde. I don't know how many of you know this story. Now recall, only electron neutrinos are produced in the reactions in the sun. Pontecorvo and his Russian colleague Gribov made the radical suggestion that as the electron neutrinos travel from the sun, interior of the sun, and journey to the earth, they periodically change their character from electron neutrino to mu neutrino to tau neutrino, back to electron neutrino, and so on. So they oscillated between 3 different personalities. That is, their flavor oscillated between the electron neutrino, the mu neutrino, and the tau neutrino. Why they should do so? Please wait, I'll tell you that. So this was the claim, that just as Dr. Jekyll transformed himself into Mr. Hyde, the electron neutrino can transform itself into a muon neutrino and the tau neutrino, and it does that periodically as it travels 150 million kilometers from the sun to the earth. But your experiment is capable of detecting only the electron neutrinos. So when they arrive at the earth, there is a mixture of 3 types of neutrinos. So 10 Dr. Jekylls left for the party. When they arrived at your house, 5 of them are Dr. Jekyll and 5 of them are Mr. Hyde. Your watchman will only let 5 of them in. You invited 10, but only 5 came in. You see what I'm getting at. So the idea of Pontecorvo and Gribov was, since Davis's experiment can detect only electron neutrinos, there will be a deficit of neutrinos. But this is an apparent deficit because you design an experiment which is capable of detecting only the electron neutrinos. So if there is an admixture of muon neutrinos and tau neutrinos, naturally your experiment will not detect them. No one took Pontecorvo's radical suggestion very seriously. The suspects were, to repeat again, the theoretical predictions of the number of neutrinos produced in the sun could be wrong, because these are very hard calculations. Second, the theoretical calculation of the rate of detection in your chlorine detector could be wrong by a factor of 3. And then there could be experimental errors that you have not accounted for. So maybe there is no discrepancy. Well, John Bacall, who was a very smart astrophysicist, persuaded hundreds of others in many, many countries to redo these calculations all over again, all the 3 calculations that I mentioned in the previous slide. And they did that over a period of 10, 15, 20 years. And they could not find anything wrong. Meanwhile, Raymond Davis continued with this experiment. He refined his experiments, he improved the error analysis. And when I first heard of Raymond Davis's result, that was in 1968, where the cursor is in this diagram. This is I can't read that, it's too small even for me. But anyway, a good 30 years or so. The red line, the vertical axis, is the flux that you would expect, and the red line is what the theory predicts. The data is shown by these black dots, and the error bars are shown. So if you draw a careful mean line, that is the green line, you see that this is 0.5 and this is 1.5, and there is a discrepancy of a factor of 3, and that discrepancy surely cannot be accounted for by the errors in the experiment. This is over a 30-year baseline. So Davis continued to maintain that there is nothing wrong in my experiment. John Bacall continued to maintain that there is nothing wrong in the theory. Therefore, there is a real discrepancy. So what do? So you design new experiments. So what new experiment can you design which would not be insulting Raymond Davis? Surely he'd got everything right in his experiment. Well, you design an experiment which could detect lower energy neutrinos, because there are more lower energy neutrinos, and see what you get. So the experiment that was planned, please remember that the chlorine experiment of Raymond Davis was only sensitive to these energies above about 0.8 million electron volt. So if you want to detect the neutrinos emitted in the proton-proton chain reaction, somebody said, why not use a gallium detector? Now, gallium is a very difficult material to get hold of. Still, there was a worldwide effort, and there were two experiments. One experiment which was done under a tunnel in the Alps mountains bordering Italy and Switzerland, in Gran Sasso underground laboratory, deep inside the mountain to reduce background noise. And this experiment was called GALEX, and that experiment used 30 tons, 30,000 kilograms of gallium. And then there was a Soviet-American collaborative experiment which was called SAGE, Soviet-American Gallium Experiment, that used 60 tons of gallium. So between these two experiments, they used every ounce of gallium that had been refined on Earth. And what did they find? They found that although this experiment could detect the low energy neutrinos, which are very large in number, therefore you would expect to have good result in your experiment, there was still a discrepancy. There was a discrepancy in the low energy neutrinos produced by the proton-proton chain reaction also. And this deepened the mystery. So newer experiments were formed, and these were neutrino scattering in water. Now, what actually scatters the neutrino is an electron. Now, here is an incoming neutrino, and at that point, it meets an electron, and the neutrino scatters off, goes off in a different angle with a slightly different energy and momentum, and the electron goes off in that direction. Now, the electron will have relativistic speeds. Therefore, it will emit radiation in the forward direction, which is known as the Cherenkov radiation, which is the optical analog of the shock wave for sound. This is the Cherenkov light. So this is what you would expect. Every time a neutrino interacts with an electron, you would expect to see a flash of light. Cherenkov light produced by relativistic electrons, which are traveling with a phase velocity, with a velocity which is greater than the phase velocity of light inside your detector, which is made of water. Now, the important thing to appreciate that this scattering can occur for every flavor of neutrino. An electron neutrino could scatter, a muon neutrino could scatter, and a tau neutrino could scatter. So this experiment can detect all three neutrinos, even though Raymond Davis's experiment could detect only one flavor of neutrino. Now, an important feature of this detector is that one is able to reconstruct the direction in which the incident neutrino came. That could be understood in the following direction. Because you know the light came in this direction, you know extrapolating in the backward direction, the neutrino came from that direction. So this beautiful detector has directionality built into it. You can actually tell from the track which direction the neutrino came from. The experiment was done in Japan. There were 3 experiments before this, but I'm going to mention only the 3rd experiment. All these experiments were done in a deep underground mine in a place called Kamiokande. There was Kamiokande 1, then there was the Kamiokande 2, then there was the super Kamiokande detector. So let me tell you very briefly, since I don't have very much time, about this experiment. It's very impressive. What you can see in that picture is an outer volume, a cylinder, containing 32,000 tons of water, H2O, and there is an inner volume containing 18,000 tons of water. So there are 2 volumes. And lining this are 11,000 photomultiplier tubes. These are not ordinary photomultiplier tubes. These were extremely sensitive photomultiplier tubes which can detect single photons. Remember, in one neutrino-electron interaction, just a weak Cherenkov light is produced. So not many photons are produced. So your photomultipliers have to be extremely sensitive, and they were 11,000 of them. So here is a very beautiful photograph inside the volume, which is being filled with water. And what you see there, which you can't see very clearly, is a small dinghy with 3 physicists going in a boat, inspecting the photomultiplier. So what you see as dots all around are these 11,000 photomultiplier tubes. And then this tank is filled right up to the brim with 15,000 tons of water. What does this result show? Precise measurements of the higher energy neutrinos by the super Kamiokande detector confirm the deficit of the higher energy neutrinos that were found in the earlier Kamiokande experiments and that were also found in the Raymond Davis experiment. But there was one slight difference. The deficit was a little less. The deficit was not 66%. The deficit was a little less. The number of neutrino events was not 33% of what was expected, but was 45% of the predicted value. Okay? Now please remember, in this experiment, you could detect neutrinos of all 3 flavors: electron neutrino, muon neutrino, and tau neutrino. They could all scatter off an electron. So the fact that this found not 33% but 45% held out hopes that maybe something interesting is happening. So let me say this pictorially. Let us say the amount of electron neutrinos expected is these 3 units. In Raymond Davis's experiment, which could detect only electron neutrinos, he detected only 1/3 of the electron neutrinos expected from the sun. But in the super Kamiokande experiment, 45% of the expected neutrinos were detected, so a little 15% more than that. But this could detect all neutrinos of all flavors. Therefore, one was left wondering, hey, look, maybe we're on to something very interesting over here. So now that's why I called it a detective story. So here is the summary. There was a deficit of neutrinos in all the experiments, in the chlorine experiment, in the gallium experiment, and in the water experiment. both low energy as well as high energy neutrinos were missing, although not in the same proportion. Is it simply that our prediction of the expected flux of solar neutrinos is wrong? So once again, we ask the same question. Could the standard model of the sun be wrong? So what is the standard model of the sun? The standard model of the sun predicts the temperature and density at various radii. And in particular, you are interested in the innermost core of the sun. You want to know what is the temperature and density profile there. Because the nuclear reaction depends extremely sensitively on the density and temperature, as I have explained in the earlier lecture. So now people said, look, I will get you the exact temperature and density profile, and I will convince you that the standard model of the sun is not wrong. And what they used was a technique known as helioseismology. Now, by 1997, we started with 1938, Hans Bethe's paper. Raymond Davis's experiment was 1968. Then we're talking 30 years later. The results of helioseismology confirm that the theoretical prediction of the sound speed, which is determined by density and temperature by Newton's formula, if you remember, was accurate to less than 0.01%. So don't doubt the standard model of the sun. So what is this helioseismology which was able to make this statement to such a precision of 0.01%? The sun is oscillating all the time. It's oscillating in millions and millions of modes. The study of that is known as helioseismology, study of the vibrations of the sun, helios. By studying these oscillations, which is a big industry now, one can infer the conditions that prevail in the interior of the sun, in particular, right near the center of the sun. One can then infer the density and temperature and the speed of sound, etc., from inverting the data obtained from helioseismology. Thus, helioseismology is an excellent tool to verify the theoretical models of the interior of the sun. And the precision to which the standard model was confirmed by helioseismology, 0.01%, virtually ruled out the possibility that the deficit of neutrinos observed in the various experiments could be due to our predictions being wrong. It simply ruled out to 0.01% is the only possibility. This strengthened the suspicion that something must be happening to the neutrinos as they travel from the sun to the earth, as Pontecorvo had predicted way back in 1968. Now I'll tell you about another interesting experiment, the experiment to detect atmospheric neutrinos. Now for a couple of minutes, forget about neutrinos from the sun. Let us concentrate on neutrinos produced in the upper atmosphere. The aim of this experiment was to directly try to vindicate Pontecorvo's suggestion of neutrinos oscillating between three flavors: electron neutrino, muon neutrino, and the tau neutrino. So let's not worry about the sun. Let's look at neutrinos from a nearby source. Nearby source is the atmosphere of the earth. Why do neutrinos come from the atmosphere of the sun, of the earth? So this is something that I've already explained. So let's now look at atmospheric neutrinos. So this grayish box is the atmosphere of the earth, some 10 kilometers in height. And a cosmic ray proton comes from some distant galaxy or a distant supernova remnant or a distant pulsar. That cosmic ray proton interacts with the nucleus of an atom in the Earth's atmosphere and produces what are called secondary particles, secondary hadrons, And these hadrons consist of pi mesons, k mesons, and all kinds of other particles. There is a shower of particles. Let us concentrate on the pi mesons. The pi meson decays to a mu meson and a mu neutrino. Now, pi mesons come in three varieties: pi plus, pi minus, and pi zero, neutral pi meson. So depending on whether it is a pi plus pi meson, this will be a mu plus. If it is pi minus, this will be mu minus, and so on. Therefore, you will produce in this decay of pi meson to mu mesons, mu neutrinos or mu antineutrinos. Now, this mu meson decays to an electron and an electron neutrino plus a muon neutrino. Okay, so the pi meson decays to a mu meson, the mu meson decays to an electron. In the process, it produces electron neutrino and muon neutrino. So let us now concentrate only on the muon neutrino. Let's concentrate on the muon. So these are known as the atmospheric neutrinos. These are the atmospheric neutrinos. Neutrinos produced in our atmosphere, triggered by an incident cosmic ray proton. All right, fine. Now let's design an experiment. Here is the Earth. Here is the Earth's atmosphere. Here is Japan, where the experiment was done. The experiment was done using the super Kamiokande detector, which I have described now. So the idea is the following. The idea is to detect mu neutrinos that are produced over there and travel a mere 10 kilometers before it reaches the super Kamiokande water detector. But a neutrino, a cosmic ray proton, could also produce a mu neutrino over here on the other side of the Earth, on top of the atmosphere over there. And that mu neutrino, that mu neutrino will not have to travel just 10 kilometers, but it has to travel another 10,000 kilometers inside the Earth. This figure that I have drawn is not to scale. The atmosphere is only 10 kilometers in width, in thickness, but the Earth has a radius of 10,000 kilometers or thereabout. So the diameter of the Earth is roughly some 20,000 kilometers, if you of that order. Therefore, these mu neutrinos have to travel a much larger distance to reach the Kamiokande detector than these neutrinos. Okay, so it's a running race. I released mu neutrinos from 2 points. One has a short distance to travel, the other has a large distance to travel. So here it is again. So the mu neutrinos over here have to travel a short distance. These mu neutrinos produced in this part of the atmosphere have to traverse a much longer distance, indeed, through the entire Earth. So, therefore, the number of mu neutrinos that you would expect to detect from the two directions would be different if neutrinos oscillated between different flavors. If mu neutrinos remained as mu neutrino, if Dr. Jekyll remained as Dr. Jekyll, then the number of mu neutrinos you would detect from this direction would be the same as the number of neutrinos you would detect from this direction. Remember that in an electron scattering experiment, I told you, the neutrino scatters the electron in the forward direction, and the electron radiates Cherenkov radiation in the forward direction. Therefore, by detecting the light and tracing it backwards, I know exactly where it came from. Therefore, I can tell from the light flashes whether the neutrino came from this direction or the neutrino came from this direction. If there were neutrino oscillation, then these numbers could be different. If there were no neutrino oscillation, then these numbers will be exactly the same. Because the cosmic ray protons coming from all directions is the same. Okay, so here is the result that was announced in August 1998. So let me explain this plot. Important thing is to appreciate that the y-axis is the number of neutrino events in the super Kamiokande detector to detect the muon neutrinos produced in the upper atmosphere. So let me explain the various things. This red histogram is the expected number without oscillation. In other words, if there were no oscillations, that is where you expect the data points to be. The black dots with error bars is the observed number of muon neutrinos. It is this histogram. So clearly, the observed number of neutrinos is different from the expected number of neutrinos if there was no oscillation. But there could be 15 other reasons why there is a discrepancy. What would be the expected number if muon neutrinos oscillated between the three flavors? And that is shown by the green histogram over there. So you see the green histogram, which is the expected number of neutrinos with neutrino oscillation, precisely corresponds to the observed number of neutrinos, and the expected number without oscillation is nowhere in the picture. So this beautiful, beautiful experiment confirmed neutrino oscillations that were predicted by Bruno Pontecorvo in 1968. Neutrinos do suffer from personality disorder. Atmospheric neutrino experiment proved neutrino oscillations. Now, this encourages astronomers. So now let's go and design a new experiment which could detect neutrinos of all flavors. And now let's catch all the neutrinos that arrive at the Earth from the Sun. Two experiments were planned and done. Experiment number 1 will detect only electron neutrinos. Just like Raymond Davis's experiment, it could detect only electron neutrinos. Experiment number 2 and 3 will detect all neutrinos, electron neutrino, muon neutrino, and tau neutrino. Now, if this oscillation story is correct, then based on Raymond Davis's very careful experiment done over a period of 30 years, you would expect E1 to detect 33% of the neutrinos, but E2 and E3 should detect 3 times E1, or in other words, it should detect the total number of neutrinos that are predicted by theory. Okay, what was the experiment? The experiment was done in Canada, in a place called Sudbury, 2,000 meters underground to minimize background events. It consisted of an inner volume of acrylic sphere, that is this acrylic sphere, and it holds 1,000 tons of water. Not ordinary water, not H2O, but heavy water, D2O, where D is a deuteron, which consists of a neutron and a proton inside the nucleus. So the inner volume, this acrylic volume contains 1,000 tons of D2O. Now this is surrounded by an 18-meter diameter Buckminster-Fuller geodesic dome on which are mounted 9,500 photomultiplier tubes, each capable of detecting single photons, very sensitive, very expensive photomultipliers. Now the whole assembly is suspended in a cavern which is 22 meters wide and 34 meters high, carved out of solid rock in the mountain and filled with 7,000 tons of ordinary water. So the inner volume contains heavy water, D2O, and the outer volume contains H2O, or ordinary water. Now here is the acrylic, Buckminster-Fuller dome, and these dots are the photomultiplier tubes. 9,500 photomultiplier tubes capable of detecting single photons produced by Cherenkov light. And what is the scattering? In E1 experiment, an electron neutrino scatters off a deuterium nucleus. Deuterium nucleus consists of a proton and a neutron. So the electron interacts with the neutron and it produces, electron neutrino interacts with a neutron and produces a proton and an electron. Okay, so there is the reaction. Electron neutrino plus neutron goes to a proton plus an electron. So what happens is that the deuterium nucleus is broken apart and two protons go flying apart and an electron which is moving at relativistic speeds and it emits Cherenkov light. And this electron, okay, so it produces Cherenkov light. Now, this process can only happen in heavy water, because if it was filled with ordinary water, H2O, then the nucleus consists of only proton. An electron neutrino cannot interact with a proton. It has to be an anti-neutrino. Please remember that lepton number has to be conserved. So you think about it a little bit. An electron neutrino cannot be absorbed by a proton. You need an electron anti-neutrino. But the sun only produces electron neutrino. The sun does not produce anti-neutrinos. Sun produces only neutrinos in the reactions that I have described to you. That is why the inner volume is filled with heavy water. Okay, now this is our experiment E1. This can detect only electron neutrinos. But now the same heavy water can be used to detect neutrinos of all flavor. And that is the neutrino interacts with the deuteron and it breaks up the deuteron. The deuteron consists of a neutron and a proton, so it splits the deuterium nucleus into a neutron and a proton, and the neutrino continues its journey. Now the neutrino thus released is captured by a deuteron producing a gamma ray, and the gamma ray scatters off a free electron, and this electron produces Cherenkov light. Please don't bother about the details. I want you to appreciate that there are two processes. One is the electron neutrino is absorbed by the neutron inside the deuterium nucleus. And the neutron transforms to a proton. So two protons come flying apart. In this breakup, there is no conversion of neutron to proton. What comes out is simple neutron and proton, which were inside the deuterium nucleus. Now, here is an actual data of a candidate neutrino event. So you see these photomultiplier tubes light up, corresponding to Cherenkov radiation. So if I now extrapolate this direction backwards, it will tell me from what direction the original neutrino came. Now, this experiment was extraordinarily difficult to do. Why? Because Cherenkov light is produced by cosmic rays also. And cosmic rays are coming all the time. Not all of them are absorbed in the Earth's atmosphere. They come and hit the nuclei in the Earth. And they produce various Cherenkov radiation. And then there is radioactivity of matter in your laboratory, in your experiment. Heavy water is radioactive to some extent. Your acrylic vessel is radioactive. Now, this mouse that I'm holding in my hand is made of plastic that is radioactive. The bottle in which you have your distilled water, Bisleri water, is radioactive. It is just that the degree of radioactivity is not hazardous to health. but you're talking about extremely sensitive detectors, and you're trying to detect an incredibly weak signal. And then there is radon gas inside mine. Radon is a radioactive material. So everything that you can steal that you use to build your experiment is radioactive. Normally you don't think of it as radioactive, but the level that we are talking about, it is radioactive. So they had to create an entire cave, which was a clean room. Now, if you go to something like a space department, or where Intel makes your computer chips, they have these clean rooms. These clean rooms are very small in volume, and they cost millions of dollars. Here you are talking about making the entire cave a clean room. So you can imagine how expensive and how difficult this experiment was. Now, unless you did that, you can't believe in the results. So here are the results. The first measurements used the experiment number 1 to detect solar neutrinos, and they detected 1/3 of the predicted electron neutrinos, exactly like Davis had done. Fine. Now, let us look at experiment number 2. Now, it took a long time to get the results, and the experiments are still going on. The experiment started around November 1999, and by May 2001, they had recorded 500 million events, 500 million events. Of these, careful analysis showed only 3,000 could possibly be candidate neutrino events. The others were discarded as background events. So you see, only 3,000 events out of 500,000 events are believable events. So a detailed analysis gave the following sensational result. The Sudbury Neutrino Observatory detected a total of 5 million neutrinos per square centimeter per second. 5 million neutrinos. Of these, 1.75 million neutrinos were electron neutrinos. This means that 2/3 of the total number of neutrinos were either muon neutrinos or tau neutrinos. So remember, experiment number 2 could detect all 3 flavors. Experiment 1 could detect only flavor 1. So this result is a sensational confirmation of neutrino oscillations. Now, here are the results stated more professionally. The results are 5.25 plus or minus 0.16 statistical error, and this is the systematic error times 10 to the power 6 neutrinos per square centimeter per second. And the theoretical prediction is 5.58 10 to the power 6 centimeter squared per second. So spectacular agreement between experiment and theory. The smoking gun was finally found. Now the results were published in 2013 based on the data obtained over a period of 7 years. So it took 7 years to produce this data, and the results were announced in 2013. Raymond Davis's experimental result was first announced in 1968. So it took a very long time, 35 years. Thus, the extremely sensitive heavy water experiment provided definitive evidence for neutrino oscillations along with the atmospheric neutrino experiment. The extraordinarily prescient prediction by Bruno Pontecorvo, made in 1968 or 69, turned out to be correct. The standard model of the sun was correct, as affirmed by helioseismology. The deficit of solar neutrinos found by Davis in 1968 was real. Davis had not made any mistake. So in 1995, some years earlier, a Nobel Prize was awarded for the discovery of neutrinos. It's a bit of a sad story. Neutrinos were predicted by Wolfgang Pauli in 1930. and it was discovered only in 1956 by Reines and Cohen. It took a long time to discover the neutrinos. And then they detected antineutrinos produced in nuclear reactors. Belated recognition for this monumental discovery came only in 1995, 30 years after Reines and Cohen had discovered the neutrino, and 65 years after Pauli had predicted it, and Pauli had long since died. By the time Clyde Cowan of this collaboration had also died, so the Nobel Prize was given only to Raymond Davis. And in 2015, the Nobel Prize was awarded jointly to Takaaki Kajita of Japan for the atmospheric neutrino experiment and to Arthur McDonald for the Sudbury Neutrino Observatory experiment. And the citation read, for the discovery of neutrino oscillations, which showed that neutrinos have mass. Now we shall pause and discuss what are these neutrino oscillations. Why should we get terribly excited about it? Well, neutrinos are created with specific leptonic flavor. In specific reactions, in decays, they are produced either as electron neutrinos or muon neutrinos or tau neutrinos or antineutrinos, depending on which decay that you're considering. But these flavor states, as they are called, electron is a flavor, muon is a flavor, and tau is a flavor, are not the basic eigenstates. They are not the states of a definite mass. Now, each flavor state is a linear combination of the more basic mass eigenstates. Now, if you have studied some quantum mechanics, you will know what an eigenstate is. Eigenstate is a state with a definite mass or energy. But you can have linear combinations producing other mixed states. So the statement that is made is that the basic states are neutrino mass eigenstates. These can be combined by linear superposition to flavor states, but the flavor states are not the basic states. So let me give an analogy. Let us consider right circular polarized light and left circular polarized light. And let us consider them as linear superposition of two orthogonal linear polarizations. As you know, two simple harmonic oscillators at 90 degrees is equivalent to a circular motion, harmonic motion. Now, let us look at this picture here. Look at the picture on the left. There it is, I got my cursor back. So here is the vertical polarization. It oscillates like this. And here is a horizontal polarization. And for this particular moment, the resultant vector is over there. Now, as the amplitude of the vertical polarization changes and of the horizontal polarization changes, this resultant vector will move on the circumference of a circle, and it will move in a clockwise direction. This is known as right circular polarized light. But if the relative phase between this vertical polarization and horizontal polarization is like this, then the resultant vector will move on the circle in an anti-clockwise direction, which is a left circular polarized light. Therefore, left circular polarized light and right circular polarized light can be thought of as linear combination of two orthogonal linear polarization with specific phase relationship between these two linear harmonic oscillators. Now, suppose the phase difference between these two linear polarization changes periodically in time. Then right circular will change to left circular will change to right circular, to left circular, to right circular in a periodic fashion. So neutrino oscillations are something like that. But in order for that to happen, some condition has to be satisfied. But before that, let me show you one other example. So he has two coupled pendulums. Just watch. Now the left one is oscillating. Now both are oscillating. Left one is stationary, right one is stationary. Both are oscillating. So the idea of that experiment is that this pendulum that's oscillating, let us call it an electron neutrino. This pendulum oscillating, let's call it a muon neutrino. So first you have only electron neutrino because this pendulum is stationary and this is oscillating. Then both are oscillating, so it's admixture between electron and muon. Then this becomes stationary and this oscillates, so it becomes a muon neutrino, and then it becomes an electron neutrino, and then it becomes a muon neutrino. So the analogy between this and neutrino oscillation was suggested by a distinguished Russian theoretical physicist. So now let's continue with the story briefly, but and somewhat fast. So the mass eigenstates are normal modes of the system, and their propagation can be described by plane waves such as shown over there. Now the important thing to appreciate is that because the masses of the, let's consider, here I'm considering only two flavors of neutrinos. Let's forget the fact there are three flavors. Just for illustration, to explain this concept, I'm considering only two flavors of neutrinos. Let's call them 1 and 2, electron neutrino and muon neutrino. So here are the mass states. These are not electron neutrino and muon neutrino. These are the two mass eigenstates, mass M1 and mass M2. Now, because their masses are different, they travel with different phase velocities. Therefore, the phase difference between these two waves will change with time. And therefore, their sums and differences, which are the admixtures, will also oscillate between two flavors. So that is shown over there. So let me explain. So these are the two mass eigenstates, and if the two neutrino eigenstates have non-zero masses, then and then only they will propagate with different speeds. If the two flavors of neutrinos have zero masses, then they will both travel at the speed of light. But at least if one of them has a mass, then this one will travel at a different speed compared to the first one. And you can expect interesting interference phenomena to occur in a periodic fashion. Therefore, the phase difference between the mass eigenstates will change with time. And that's what is shown over there. So you have a red and blue mass eigenstates. This is blue, not very blue in this diagram, and this is the red mass eigenstates, and they travel with different velocities. Let us say, by definition, let us say that when they are in phase, that it is an electron neutrino, and when they are in anti-phase, it is an muon neutrino. Let us just adopt this convention. So you see, this is time moving from left to right. So I start out with an electron neutrino, which is an admixture of two mass eigenstates. They are in phase, therefore I call it electron neutrino. Little later, it's an admixture of electron neutrino and tau neutrino, or mu neutrino, or type 1 neutrino and type 2 neutrino, excuse me. And over here, I'm going to call it the muon neutrino. Over here, I'm going to call it again an electron neutrino, and so on. So there is a periodic oscillation in the flavor as these two mass eigenstates propagate. All right? So that's the idea here. So the flavors oscillate between electron neutrino and muon neutrino as the neutrino propagates. This phenomena is known as neutrino oscillation. Let me stress once again, the basic eigenstates or the mass eigenstates, if neutrino have masses, then they will propagate with different velocities, and the phase difference will change periodically in time. Therefore, just as left circular will become right circular, will become left circular and right circular, similarly here, it will become in phase, out of phase, in phase, out of phase, in phase, and out of phase. So it will go from electron neutrino to muon neutrino to electron neutrino, and it will oscillate in flavor. So the neutrinos were produced in the sun as electron neutrinos. Sun only produces electron neutrinos. As they travel the 150 million kilometers, their flavor oscillated between electron neutrino, mu neutrino, and tau neutrino. So when they arrived at the Earth, there was an admixture of all three flavors. And since Davis's experiment could detect only one flavor, namely electron neutrino, naturally he detected only 1/3 of the expected number of neutrinos. But the Sudbury heavy water experiment could detect neutrinos of all flavors, and therefore it detected the expected number of neutrinos. So let us now conclude. Neutrino oscillation is a very simple consequence of quantum mechanics, of mixed states. And there is no reason to get excited about it on that account. But the important thing is, for this oscillation to occur, neutrinos must have a mass. All right? And that is the sensational moral of the story. The present data imply that the mass of the electron neutrino is about 100 million times smaller than the mass of the electron. But it is non-zero. People have directly tried to measure the mass of the neutrino. It's very hard. As of now, the claim is that the mass of the electron neutrino is 100 million times smaller than the mass of the electron. And remember, electron is the lightest of all the particles. But it is non-zero. A non-zero mass requires a major revision of the standard model of elementary particle physics. What is the standard model of elementary particle physics? Well, there are four basic forces in nature: electromagnetic forces, weak forces of radioactivity, strong force that binds the nucleus together, and of course gravitational force, which we shall set aside. But these three forces, which apparently seem very different in our present-day universe, namely electromagnetic force, the weak forces of radioactivity, and the strong force of nuclear binding, were not three separate forces in the early universe. all three forces were unified into a single force, and there was a single unified theory. How do we know that? By doing experiments with high energy colliders, you simulate the conditions that prevailed in the very early universe. And there you can verify that the predictions of such a unified theory of these three forces. And that unified theory of weak electromagnetic and strong forces is known as the standard model of elementary particle physics today, and it is enormously successful. Unfortunately, in that theory, the neutrino cannot have a mass. It is not allowed to have a mass. Therefore, if the solar neutrino experiment and the atmospheric neutrino experiment have confirmed that neutrinos do oscillate, then neutrinos must have mass. And therefore, something must be wrong with the standard model of elementary particle physics. Now, we started by asking why the sun shines in the first lecture. Eddington answered it 100 years ago in 1920. It took nearly a century to prove that he was right. He detected the neutrinos now of the right number. Now, in the process, we have discovered that fundamental physics needs a major revision. Now, astronomy has played a major role in the development of physics for centuries. The law of gravitation, the finiteness of the velocity of light, spectroscopy, the discovery of helium, the first verification of time dilatation, the first proof of gravitational radiation, etc., are some examples of fundamental discoveries in physics that came from astronomy. Once again, a major input to physics, namely the standard model of physics needs a major revision, comes from astronomy. And with that, I shall conclude this lecture. In the next lecture, we shall discuss another extremely exciting and very topical subject, namely gravitational waves. Till then, thank you very much for your attention.